Hello everybody, getting ready to do lesson 5.2 part 1 of pre-calculus math today, the classwork version of this lesson. If you have any questions or need course materials, email me here, animatedpowerpointmathvideo@aol.com. 5.2 part 1, we have 10 points here of notebook taking. If you need notebook note-taking guides, email me at the email address. And then 32 points here for classwork today. Teachers, today's bell work is use a graphing calculator to construct a table of values for the function, then sketch the graph of the function, identifying the asymptotes of the graph. So we have this one here, students, and this one here. Give your students 5-6 minutes for that. Teachers. Okay, welcome back for your solutions for today's bell work. So this is your table, students. This is your values that you should have on your calculator. This is your graph that you should have for 2x plus 3. And your asymptotes, horizontal asymptotes, be y equals 3. Your asymptote be right here. You put like a dotted line there, that'd be great. And then down here for this one, here's your table of values. Here is your graph here for f of x equals negative 2 to the x minus 3, and then an horizontal asymptote will be y equals 0, so it'll be your y-axis would be your asymptote, and so it'll be y equals 0 as x goes to negative infinity. So as this goes to negative infinity, you shall see that the y-axis is your horizontal axis. Okay, into our first notebook page here, verifying trigonometric identities. In this section, you will study techniques for verifying trigonometric identities. In the next section, you will study techniques for solving trigonometric equations. The key to both verifying identities and solving equations is your ability to use the fundamental identities and the rules of algebra to rewrite trigonometric expressions. Remember that a conditional equation is an equation that is true for only some of the values in its domain. For example, the conditional equation sin x equals 0 is true only for x equals n pi, where n is an integer. When you find these values, you are solving the equation. So on the other hand, an equation that is true for all real values in the domain of the variable is an identity. So an equation that is true for all real values in the domain is an identity. For example, the familiar equation sin squared x equals 1 minus cosine squared x is an identity. It's true for all real numbers of x, for all real numbers of x. So it is an identity. Verifying a trigonometric equation is an identity is quite different from solving an equation. There is no well-defined set of rules to follow in verifying trigonometric identities, and the process is best linked to practice. So practice makes perfect in finding identities. Guidelines for verifying trigonometric identities. Work with one side of the equation at a time. It is often better to work with the more complicated side first. 2. Look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. 3. Look for opportunities to use fundamental identities. Note which functions are in the final expression you want. Sines and cosines are up. Identities. Note which functions are in the final as well as do secants and tangents and cosecants and cotangents. So which functions you end up with will determine which kind of identities you're solving for. Remember that. Try to force an identity. 4. When the preceding guidelines do not help, try converting all terms to sines and cosines. 5. Always try something, even making an attempt that leads to identity provides insight. Verifying trigonometric identities is a useful process when you need to convert trigonometric expression into a form that is more useful algebraically. When you verify an identity, you cannot assume that the two sides of the equation are equal because you are trying to verify that they are equal. As a result, when verifying identities, you cannot use operations such as adding the same quantity to each side of the equation or cross multiplication. Cannot. So verifying a trigonometric identity. Verify the identity here. We have secant squared theta minus 1 over secant squared theta equals sine squared theta. Because the left side is more complicated, start with it. So secant theta minus 1 over secant squared theta equals tan squared theta plus 1 minus 1. So over secant squared theta, this is equal to that. And then tan squared theta over secant squared theta simplifies. So tan squared theta, these ones cancel each other out. So tan squared theta over cosine squared theta, this is a reciprocal identity here. Cosine squared theta, secant squared theta is 1 over cosine, remember? So if you flip it up, then you'll get this product here. Okay, moving on into here, we have sine squared theta over cosine squared theta times cosine squared theta. These will cancel out. And then you end up with sine squared theta, which is your simplified solution there. Let's try one now. Cosine beta minus sine squared beta equals 1 minus 2 sine squared beta. So we need to verify this identity here. And then down here we have something cosine squared sine, something somewhat different here. Okay, for these verifying these identities here, we're going to verify that this is going to equal this. And the way we need to, first thing we need to do is bust up this 2 sine squared beta. So the way to do that is to move this, one of these negative sine squared betas over here. And then we're left with 1 minus sine squared beta when we move one of these sine squared betas over here. And that is equal to 1, actually. So 1 minus sine squared beta equals 1. And then we have a sine squared beta, and 2 negative sine squared betas would equal negative 2 sine squared betas left over from that one. And then down here, again, we need to bust up this cosine, this 2 cosine squared beta minus 1. So the way we do that is, this is positive, so it's cosine squared beta minus a 1 minus cosine squared beta. So we bust this up into 2, it's a negative, so we have their negative 1, and then our negative cosine squared beta, and then when we combine back, we get cosine squared beta minus 1 here too. So when we bust up these 2's here into this kind of format here, we can go back to this. So we can bust this 2 sine squared beta up here and bust up this 2 cosine squared beta down here into these statements here. So this going through that equals back to that again. There can be more than one way to verify an identity. So we have secant squared theta minus 1 over secant squared theta equals secant squared theta over secant squared theta minus 1 over secant squared theta. Rewrite as a difference of fractions. So we're going to rewrite this as a difference of fractions here. We separate these two parts of the numerator into this over here. And then when we recombine it, this over here will equal 1 minus cosine squared theta here, which is 1. This becomes 1, and then this is 1 over secant squared theta, which is the same thing as cosine squared theta. So we have reciprocal identity, and then this becomes sine squared theta, Pythagorean identity. And then remember that an identity is true only for all real values in the domain of the variable. For instance, in example 1, the identity is not true when theta equals pi over 2 because secant squared theta is not defined when theta equals pi over 2. So you have to remember when you go through this process here of verifying identity that none of these denominators are 0, to make sure that that is the case here. Let's try another example here. We have combining fractions before using identities. So to verify this identity, 2 secant squared alpha equals 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. So the right side is more complicated, so we'll start with it. So 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha equals, when we combine these two together now. We're going to combine these two together. We're going to add our fractions. This is our common denominator. And then we have this up in our numerator now, meaning we cross multiply here to get our numerator. And then we need to combine that. And then we get 2, because both of these are actually equal to 1. So we get 2 over 1 minus sine squared, or alpha, I'm sorry, it's alpha. So 2 over cosine squared alpha is a Pythagorean identity. The 2 secant squared alpha is a reciprocal identity. Using a graphing utility to create a table that shows the values of y1, which is 2 over cosine squared x, and y2, which is 1 over 1 minus sine x plus 1 over 1 plus sine x for different values of x. And you can see here when you have y1, y2 at -5, you have identical values there. See where else you're at 0.25 you do, at 0 you do. So they're basically, they are the same function. So that verifies it there. You can check it on your calculator. So use the table feature of graphing utility to check your result numerically. So our first one up here, we need to add these together by using identities. So we're going to add this up here by using common denominators. We're going to multiply these two together here. Sine x plus sine y times cosine x plus cosine y. And then you get this gnarly numerator up here. And then when we multiply through, we get squares up here. Cosine squared x minus cosine squared y plus sine squared x minus sine squared y. And then these both will equal to, see, cosine x, well, when you group these together, they become 1. So you have a 1 and minus 1 over this here, this denominator here, and that equals 0. So that verifies this situation here. And then down here, for that one, I'll leave that for you to do. So that is our lesson for today. Email me here for questions, class worksheets, note-taking sheets, and other information for the course. Thank you very much.